Hey, Sebastian. Recording? Okay. So today we're going to be going over problem 9.4 from the book. So it's this electrical circuit here. And we're going to do some frequency domain analysis of it. So first a little bit of introduction. So we've got the circuit, has an input voltage, yada yada. And so we're going to work our way into finding the transfer function. So part A, so we find the Laplace transform of our governing equations. So they've already done it there for the resistor, is VI of S minus VO of S equals R times I of S. And so all they've done is they've taken the, make sure my stylus is working, is they've taken the time domain equation of VI minus VO equals RI, and they took the Laplace transform of that. So we're going to do the same thing for the inductor and the capacitor. So does anyone here remember the equation for an inductor that talks about the voltage and current through an inductor?
Is that one the 1 over L integral of the voltage? Or no?
That is right. It's so it looks like I've got the answer of the Laplace thing in front of me. Let's go to, that sounds right to me. I think it's like voltage over L is equal to the integral of your current, as I recall. Yeah, let's see here. That is right. So for an inductor, your voltage drop over the inductor is equal to L times, not the integral, but the derivative di dt. So we're going to take the derivative of that, so we're going to take the Laplace transform of this. So our voltage drop is VO minus VI, sorry. So our inductor, we've got, so the voltage drop over the inductor is right here. So it's VO minus that node VC. And so that's equal to L times di dt. So what do we get when we take the Laplace transform of these terms?
Is it just S for one of them? Like, is it just LS,
so the
big Y of S equals VC minus VO? Or
yeah,
minus
so
VC?
most of what you said is right. So we've got capital VO of S minus capital VC of S, and that's this left-hand side there. And then you said multiply by S, and that's right. When you have the derivative of a function, the Laplace is just, so L is a constant, and then it's S times I of S. So that's the derivative there, or that's how you take the Laplace transform of a derivative.
Can I ask why we have I of S in both of these?
In both of them?
Yeah. Why is it I of S instead of like Y of S, like we're used to?
So we just use I because we're talking about the current.
Okay.
So for the resistor, we could have written this as I of t, like VI of t minus VO of t equals R times I of t. So everything's a function of time. And then you just take the Laplace transform of I being the current. And generally the convention is the Laplace, like if you use a lowercase letter to indicate something in the time domain, you use the uppercase of that same letter to indicate that you're in the Laplace domain.
Okay, thank you.
Does that clarify? Does that answer your question?
Yeah, I just remember always doing Laplace transforms with like y of capital Y of S. Like just
Yeah,
the
and that's because
Laplace
you
transform of a regular random ODE and not having them apply to any kind of real world scenario.
right. And yeah, and use like a regular ODE, you're probably doing something like y double dot plus y dot, right?
Yeah.
Usually that would go to like s squared y of s.
Exactly.
Similarly, you do like x double dot would be like an s squared, and usually you would do like a capital X of s.
Okay.
When you do the Laplace transform.
Okay. So because we're doing
Cool.
we're trying to figure out like all of this as a function of current. That's why we have capital I of S.
Yeah,
Did I
so
say that?
right now we're working with voltage and current. So these are V of S on the left-hand side, and then I of S is just the Laplace transform of the current.
Okay. Thank you.
All right. So now for a capacitor. So the general equation, does anyone remember the general equation for a capacitor? I think, let's see here, what do we use? Yeah, so I'm on page 84 here. So I see, then that's just the table of all of your electrical equations. So your current is equal to your capacitance times dV dt. And so in this case, we have, so what's our voltage going over our capacitor? It's the voltage drop there.
Is it VC minus 0?
That's exactly right. So our current going through our capacitor is equal to C times dVC dt. And so if we take the Laplace transform of this, we take the Laplace transform of little I, and that's a capital I of t, or of s, sorry. And so that equals C times, and then the Laplace transform of a derivative, same as what Sebastian said earlier, is just S times capital V sub C of S. Okay. So then it wants us to separate this out into matrix form. So we have some matrix times V naught of S, VC of S, I of S, and so it wants us to isolate V I of S. And we know that our second two equations here don't have VI of S in them, so that's why we have zeros. But we just need to separate out the coefficients of these three terms. So the coefficient in front of, on our inductor for V naught of S is just 1, right? Sorry, that's a bad one. Okay. So what's the coefficient for VC of S?
-1.
Wait, why
That's
in
right.
the line above it was the V naught 0?
So the VC is 0 in the line above it. So we have VI of S is what we're looking at here. So we move everything to the other side and we have so if we move this over here, we have a +1 times VO of S plus 0 times VC of S plus R times I of S.
Oh, okay, thank you.
You see that? Okay, perfect. And then the coefficient, if we isolate our, so if we move everything to the left-hand side on our second equation, the coefficient for I of S is -L times S. And then same process with our with this last equation. We have no coefficient in front of V naught of S. We're going to go ahead and move, subtract the I over to this side. So what's our coefficient in front of VC?
Is it just CS?
That's right, it's C times S. And then our coefficient in front of I is just going to be a -1 because we moved the I over. Okay. Any questions about that?
So we moved the I over because we needed to make it the whole equation equal to 0.
That's right.
Because of because of the column next to VI of S. Okay.
That's right. So then part B, so it solved the matrix equation for the unknowns. And so all they did is they solved for this column of V naught, VC, VI. They used just a matrix inverse. And so you can see what they came up with there. So then part C wants us to find the transfer function of V naught of S over VI of S. And so for that, we're going to use the first row of this equation here. So V naught of S is going to be equal to S squared C times L plus 1 over S squared C L plus S R C plus 1. And all I did is just multiplied out the first row of, or just extract out the first row of this matrix from part B. I'm sorry, so then that whole thing is multiplied by VI of S. And then, so we've got V naught equals this times VS. So to get V naught over VI, we're just left with this fraction there. So our transfer function is S squared C times L plus 1 over S squared C times L plus S times R times C plus 1. And that's our transfer function. Questions about that?
How is that our transfer function? I'm a little confused.
Sorry, I didn't hear the first part. Can you repeat that, Sarah Lynn?
Yeah, you're good. The transfer function. So I see that we solved for V naught, but isn't it supposed to be V naught over? Oh, okay. So VI was in the bottom. You just canceled those out. Okay.
Yeah. So I just divide this VI over to the left-hand side. And then we're just left with that fraction there.
Got it. Thank you.
Perfect. Good question. All right. So now what we're going to do, we're going to move on to part D. So it says find the magnitude of g of j omega by calculating the magnitudes, blah, blah, blah. So for S, we're going to plug in j omega. And then then what we're going to be left with in the numerator, it's going to be a complex term, and we're going to find the magnitude of that term. So S squared C L plus 1, we're going to evaluate that at S equals j omega. And so that's just going to be j omega squared C times L plus 1. And that's going to be, so negative omega squared C times L plus 1. That's because, so j squared is -1. So everything here is actually a real term. So because this is real, what's the magnitude of this term?
Is it just the square root of like the squares below it?
Right. So yeah, so it's actually just the square root of this term squared. So you just get a 1 minus CL omega squared. The answer key here has this squared and the whole thing under a square root, which is somewhat redundant. But we have no imaginary term. If we did, then we would do a Pythagorean theorem with one side being the real terms and one side being the imaginary terms, which is what they did down here on the numerator for us. But we don't actually need to do that, so we can just write it as 1 minus C times L times omega squared. Any questions about that? Okay. So we're going to move on to part E. So it says use the previous expression, g of j omega, to estimate the magnitude of very small and very large omega. So to estimate the magnitude at low omega, we're just going to take the limit as omega approaches 0 of the magnitude of g of j omega. And if we just plug in omegas for all of our terms here, we get 1 in the numerator and square root 1 minus 0 plus 0 in the denominator. So we just get 1. Okay. Questions about that?
Can you explain how we got that?
Yeah, so the how we evaluated the limit, or why we did the limit.
I guess like what I'm seeing. Oh wait, okay, there's a 1 down there. I was thinking it would be undefined, but I see the 1 now in the denominator.
Oh, yep, right there. Perfect. Okay, so now we're going to take the magnitude as, so take the limit as omega approaches infinity, and this will be the magnitude of g of j omega at very high frequencies. So we're just going to take this limit. So we get, it's going to be, so if we take the limit as omega approaches infinity, I'm going to go ahead and, so 1 minus CL omega squared over square root 1 minus CL omega squared plus RC omega squared. So if we just plug in infinity, we get 1 minus infinity in the numerator and 1 minus infinity squared plus infinity in the denominator. So that's probably negative infinity. So we're going to take the derivative of both of these. So this, do we want to spend time evaluating the limit? Or do we want to know that this is the process and move on? Quick poll. I see 3 of you. Is that right? Just 3 of you here?
So you would just use L'Hopital's rule and then take the limit
Yeah.
again?
Just, that's exactly right. The answer is going
This
to come
seems
out
like
to,
sorry, I was just
Go
going to say,
ahead.
this seems like a complicated derivative, at least the denominator is. Will we see something like this on an exam or on the homework or whatever?
I'm not sure what's on the homework. I would assume that like anything that requires taking a, like, so on the test there was on the previous test there was an integral that you had to do. So you should know how to do derivatives, but I wouldn't assume that it's going to be a big part of the problem necessarily. We wouldn't be testing you on that.
Okay, thank you.
So yeah, I think we can just kind of intuit. We have an infinity squared in the numerator and a square root of an infinity to the 4th in the denominator. So both of the infinities are to the same order. So we can predict that the limit comes out to 1, and in fact it does. Any questions about that?
It comes out to 1 because it just becomes infinity squared over infinity squared, right?
Yeah, that's essentially what happens.
Okay.
Or negative infinity squared over negative infinity squared.
Okay.
Okay. So this next one, using some data, they made a Bode plot relating the magnitude and phase to the input voltage. And so that's here on this next page. Have we gone over Bode plots in class yet?
Not
You
quite.
mentioned it once or talked about it in class, but I never quite understood why.
I did it yesterday.
Okay. Yesterday?
Like he did the,
Okay.
yeah, he did, like, he made one at the end of class.
Got it. Okay. So this right here is a Bode plot. You can see this top plot. We're plotting magnitude ratio. So our output magnitude over our input magnitude. So at very high and very low frequencies, it's 1, kind of how we just determined from the previous problem. At a frequency of 1 radian per second, down here, it's 0. So we actually get no output. And then the bottom plot is your phase angle, your phase offset between your input and your output. as a function of your input frequency. So that's what a Bode plot is. It'll show it's usually going to be the magnitude ratio on the top, the phase offset on the bottom plot, with your frequency on a log scale on your x-axis is going to be a Bode plot. So they've created it here for you. I think maybe later on in the class we'll be making our own. There's a MATLAB command to create a Bode plot, and we'll be able to go over that. So the first thing we're going to do, it says classify the filter by selecting one name in the first column below. So at low frequencies, we have an input. We have a high magnitude ratio, or relatively high magnitude ratio, where we get V out is as big as V in. And then again, at high frequencies, we have the same thing. We have a high magnitude ratio. And then at the middle frequencies, in the middle band, we have a low magnitude ratio. And so at low frequencies, our response is filtered out. So what type of filter do you think that is?
Is it high pass?
So a high pass filter you'd have a good magnitude ratio up at the top, and you'd have a low magnitude ratio at low frequencies. So this right here would be a high pass filter.
And then a low pass filter is just like mirroring that, right? Like it goes with the
Yep,
thing.
so a low pass filter would look like this,
So
where you
this
have
be a-
high magnitudes at low frequencies.
Would this be a notch?
What was that? That's right. This is a notch. It's a band stop. So at the middle frequencies, we have nothing. A band pass is the opposite of what we have here, where at the middle frequencies, you have a high magnitude ratio, but at very high and very low frequencies, you aren't letting anything through, you're filtering it out. So this is a notch pass filter, or a notch filter. Questions about that?
Can you explain what band pass is again?
Yeah, so band pass has a specific band of frequencies that it's going to allow through the filter. So what I've drawn, so here, so basically you'd have high frequencies at a certain range, and then your magnitude ratio would fall off if you fall outside of that band. And you can design them to have bands that pass anywhere you like. So if you need your frequencies that are about 0.1 radians per second, you would do something like that. Or if you needed about 10, you would design a bandpass filter that's something like that.
Okay, so then notch is if you want like the two extremes.
Mm-hmm.
Okay.
That's right. Okay, any other questions about this? Okay. So it says, for the filter type you chose in the first column, determine the value for the associated specification. In the second column, the associated specification. Okay, so the gap width. So the filter type, so we have a notch frequency, or we have a notch filter. And so the question is, what is the gap width of this filter? Let's see. So you use 0.707 for deciding cutoff frequencies. So 0.707. So you can see we have a magnitude ratio of 0.707 here and 0.707 about right here. And so what we're looking for is the width of this gap. So you can see it's from 10 to 0.1 radians per second. So that's approximately 10 radians per second is the width of that gap. And so that's like the specification of this notch filter. So you have a notch, and then when you're designing it, you're going to ask yourself, how wide should this notch be? And that's what we have here is 10 radians per second. So there's 10 radians per second of frequency that's not going to pass through this filter.
Question, what is...
Any questions about that?
Or yeah, if we were doing cutoff frequency, how would we... I guess what's the difference between the different specifications in the second column?
So it says, so here we're using 0.707 for your cutoff frequency. That's an important number. I can't remember exactly what that comes from. It might have something to do with the logarithm or something. 0.707 is generally your cutoff. So if you have I'll go ahead and clean up this graph here. So if you have a low pass filter, then your plot would look something like this. And your cutoff frequency is wherever your magnitude ratio drops below 0.707. So the way I've drawn it, it's about right here. And so it'd be there, so it'd be about 0.2 radians per second on this log scale is our cutoff frequency for a low pass filter. Same with a high pass filter. The way I've drawn it here, 0.707 radian, 0.707 comes about right there, which is about 2 radians per second where I've drawn it. Does that answer your question?
So
Sebastian?
each thing in the second column is paired with the first column, I guess.
Yeah.
Okay.
Yeah,
So
I
didn't
low
know
pass filter has a specification of cutoff. Yeah.
Okay. I didn't know if
and your
that
band
second
pass, their
column was...
specification is your bandwidth.
Yeah, I didn't know if that second column was its own separate thing we had to choose from. Whether it was a notch cutoff frequency
weird little thing.
Okay, thank you.
Any other questions? Okay, we're going to move on to the last problem here. So it says estimate the steady state output voltage when the input voltage is 8 sine of 3t. So your result should be solely in terms of numerical values and the function of t. So basically, our output is going to be some magnitude ratio times the amplitude of our input. So it's going to be something times 8 sine, and then it's going to have the same frequency, 3t, but it's going to have some phase offset. And so we're going to take these values off of our Bode plot. So when our frequency is 3, what's our magnitude ratio?
$75, I think.
So 3 on our log plot. So if I zoom in here, so on this log plot we have 1, so then 2 is here, 3 is here, 4, 5, 6, 7, 8, 9, 10. So 3 coming up to here is about right there on our plot. So it comes out to about 0.25 is our magnitude ratio at 3 radians per second. So 0.25. So we're going to get a quarter of our input amplitude, which is 8 for this case. So what is our phase offset at 3 radians per second?
Is that 175?
It is 75.
Okay.
Sorry, I wasn't sure where you got that, but yes, it is.
Yeah, I was looking at the wrong plot then.
Right there. So 3t plus 75 degrees. All right. Any questions about that one?
Yeah, one question real quick. Why is it 8 sine 3t? I guess where did the 8 and the 9 and the 3 come from?
So that came from our input here. So we know,
okay.
so
I didn't see that part of the question.
So it told us what our input is 8 sine 3t. So then we multiply our magnitude ratio by 8. And then the 3 is the frequency that we're looking for on our Bode plot.
Okay, I didn't see that part. Thank you.
No problem. Any other questions? Okay. I'll go ahead and